We have with us today to kind of go between these two sessions, what we call a Goddard Plus speaker. You know, it's a shorter segment, but still want to get these words in. So we have David Grinspoon, senior scientist at the Planetary Science Institute. He's an astrobiologist who studies the possible conditions for life on other planets. Let's see, he's been featured on dozens of television and radio shows, and he's also an award-winning musician, currently leading the House Band of the Universe. So look for that on Spotify. David, I turn it over to you.
Thanks very much. First of all, news flash, I'm no longer at the Planetary Science Institute. As of 6 months ago, you can see my title on the bottom of this slide. I'm now at NASA as the Senior Scientist for Astrobiology Strategy. And I've been given 15 minutes here. Thank you. I've been given 15 minutes here, and several people have already told you things that I'm going to address, which makes it even more challenging. I'll try to get to some of those topics, but what I thought I would do is give a very brief sort of history of astrobiology that in a way connects the two topics that we've been hearing about and we're about to hear about, the astrophysics observatories and exoplanets and the planetary exploration to come. And astrobiology is sort of a natural connection between the two. And you know, in the spirit of the, there's this reduced Shakespeare company you may have heard of that does the complete works of Shakespeare in 20 minutes. So in the spirit of that, I'm going to give here a greatly reduced evolution of astrobiology. Now, the questions of astrobiology, of course, are ancient and sort of endemic to being human. As conscious beings in this universe, we naturally wonder how we fit in and whether there are other beings and maybe other conscious beings out there. But of course, as our awareness of the scale of the universe and how we fit in has changed, the nature of those questions has changed as well. And did I miss a slide here? Oh, no, I didn't. Okay, and yeah, and so it's hard to know where to begin this history. I'm going to begin with the present by just reminding you that this is a really exciting time for astrobiology. In the 6 months I've been at NASA, so much is happening. We've returned samples from a carbonaceous asteroid, and the preliminary analysis of those samples is already telling us some really interesting things about the way that the organic building blocks of life were formed in space and delivered to Earth and delivered to other planets. We are currently exploring with the Perseverance rover an environment on Mars that was clearly once habitable, and we're collecting rocks there that we're going to be returning to examine in laboratories on Earth. As you've just heard a little bit about, we are also with the James Webb Space Telescope making some of the first observations of potentially habitable extrasolar planets, which is amazing and which is very promising. It's showing that the technique works, the spectroscopic identification of potential biosignature gases on exoplanets, which is very promising for the plans we have for future observatories, which you've been hearing a little bit about. And finally, we are doing amazing new things in the solar system, including later this year, we're going to be launching the Clipper mission to Europa. So it's really pretty tremendous time in astrobiology discovery right now. But you know, where did all this begin? Arguably, as I mentioned, these are ancient questions, but arguably the scientific roots of modern astrobiology began in the decade before space exploration, when space exploration was being anticipated in the 1950s. And one real potential starting point is the Miller-Urey experiment, where what were seen as likely constituents of the early atmosphere of Earth were given what seemed like likely energy sources, and indeed, under those conditions, it turned out to be very easy to create some of the organic building blocks of life. So this was really promising, done by Miller and Urey. Stanley Miller, just a grad student at the time. His advisor, Harold Urey, the Nobel Prize winner, who was really one of the founders of modern planetary science, also happened to be the PhD advisor of my PhD advisor. This led to a wave of optimism about finding life elsewhere. Miller and Urey wrote that they fully expected, partly based on these results, that Mars and Venus both have life. Because it's so easy to make the stuff of life, and what they understood about the environments of those other planets at the time was consistent with this. They also wrote about what they thought were the early environments of Venus and Mars, and again, they were pretty sure there was an origin of life on all these planets. So this was part of a wave of optimism, and as we'll see, there have been sort of successive waves of optimism and then disappointment and pessimism, and our expectations have sort of oscillated as we've learned more and perhaps overinterpreted a lot of early results. The first actual successful spacecraft to another planet was Mariner 2 to Venus, and the results of Mariner 2 in a way were seen as a big disappointment. I mean, it was, from a planetary science perspective, it was tremendously successful. There was basically one instrument to study the atmosphere, a microwave radiometer, and it showed unambiguously that Venus is very, very hot on the surface, too hot for water or organic molecules. So it was a success for planetary science, but the way that it was received, certainly in the press, this is the New York Times, in December 1962, and you can see the title of the editorial about this result was "Venus Says No." And if you read on the bottom right here, they concluded that Mars now remains our only hope of turning our universal dreams into reality. And the evidence so far is not very encouraging. The message from Venus may mark the beginning of the end of mankind's grand romantic dreams. You know, what a bummer. But you know, we were learning, and the next thing we did was send a flyby to Mars with Mariner 4 in July 1965, and again, in some ways, it was seen as a big disappointment. Mariner 4 imaged in decent, almost decent resolution, about 5% of the surface of Mars, and yet that small sliver happened to show an area that was very sort of lunar-like and cratered and seemed sort of geologically dead, and that led to, again, kind of some sense of disappointment among those that were thinking that maybe Mars was a promising place for astrobiology. President Johnson said, well, it just may be that life as we know it is more unique than we may have thought. And the editor of Science at the time was even more harsh. He said, in looking for life on Mars, we could establish for ourselves a reputation of being the greatest Simple Simons of all time. So that was not a high point for our expectations of life elsewhere. But things changed when we actually sent an orbiter to Mars and got to see a much more planetary view. Mariner 9 in 1971 imaged much of the surface and showed a really much more varied and complex and interesting place than we had thought. Lots of evidence of at least ancient fluvial activity, dried up rivers, channels, interesting complex polar history, volcanic history. You could see hazes and clouds and weather in the atmosphere. So Mars turned out to be much more complex. And this led to the idea that it was actually led to, in retrospect, some wrong ideas about Mars. One of the popular ideas, popularized by Carl Sagan, was that Mars went through these periodic climate changes where it would become Earth-like because of the orbital cycles, the climate oscillations over millions of years, where there would be these sort of intermittent Martian springs, and there could be organisms on the surface waiting for the right conditions. And this body of thought out of Mariner 9 basically led to the origin of the Viking mission, which was our first attempt to land on another planet and actually search for life. And Viking, again, was an incredible success that in some ways some people perceived as a failure, which, I mean, Viking was an amazingly successful mission in so many ways. Our first Mars lander, we learned so much that's still foundational to our knowledge of Mars. But the biological experiments were perhaps a little bit narrowly focused on finding sort of Earth-like organisms in the surface soils of Mars, and they, as far as the investigators could conclude, were not there. And so we have this quote from Norman Horowitz, who was one of the lead investigators on Viking, saying the failure to find life on Mars was a disappointment, but also a revelation. It is now virtually certain that Earth is the only life-bearing planet in our region of the galaxy. We have awakened from a dream. So again, waves of optimism, pessimism. Now, I'm not going to go through the whole history of Mars exploration in what's left of my 15 minutes here, but what I'll say is that in the wake of this, as you know, we've had many tremendously successful orbiters, landers, rovers, and our knowledge of the history and complexity of Mars has really deepened since then. I mean, one of the lessons of Viking, really the meta lesson of those experiments, was that we needed to learn a lot more about planets and a lot more about life before we could go about designing life detection experiments that really had a chance of finding something. Viking exposed our ignorance and our assumptions. So the good news is that in the interim decades, we've learned a lot more both about planets and about life. And of course, we've found lots of evidence for early habitable environments, rocks on the surface that could only be formed in the presence of running water, meandering rivers, evidence of all kinds of layered sediments and all kinds of very rich evidence for a fascinating and complex aqueous history in the early history of Mars that is very promising, at least for early life on Mars, and then some interesting questions and a wide array of opinions about whether current life on Mars is something we should search for or not. But certainly the notion that Mars should have had an origin of life and early life, if we are correct about what it took on Earth, is a pretty mainstream idea that we are in the process of testing. Now, during all these decades of exploration, first of all, we needed to invent planetary science. With Mariner 2, there was no such thing. And it was this kind of interesting hybrid field between the techniques of Earth science and the perspectives of space science. But during all that time, astrobiology was really exobiology, and it sort of existed on the fringes of this science. People were pursuing it, some early pioneers like Carl Sagan and Chris McKay and Lynn Margulis, but it wasn't really embraced as a central part of NASA science. It was something you could do. NASA did support exobiology, but it was something you couldn't really build a career out of unless you were doing something, sort of more reputable as your main science. That really changed in the 1990s because of a number of developments that made the possibility of life elsewhere seem more promising. So what happened in the 1990s? There were several areas of discovery that kind of converged and made the notion of finding extraterrestrial life seem more promising. And one, of course, was the gathering evidence of extremophile organisms on Earth, that our previous assumptions of the narrow range of conditions that life needed were wrong. And we were finding organisms that lived in places that were much colder, hotter, more acidic, you name it, devoid of light, and using seemingly bizarre energy sources, that life was much more adaptable than we had ever thought. At the same time, ocean worlds became a scientific reality because Galileo was in orbit around Jupiter, and the imagery and other data from Europa made it clear pretty certain that Europa has the largest ocean of liquid water in the solar system, and as far as we could tell, all the conditions required for life. Also in the 1990s, we began to discover enough exoplanets to realize that, oh yeah, the planets in our solar system are actually a minuscule, trivial component of the complement of planets in the galaxy. So that, vastly changed the picture as far as the amount of real estate where life could be evolving. But finally, the sort of culminating event it took place in 1996, or I guess 1997, with the report that what we in the business call the Mars rock, which is ALH 84001, a Martian meteorite discovered in Antarctica that was reported in Science magazine to have microfossils and other evidence of life. Now, even though it turned out that in the long run, that evidence probably has other explanations, and the scientific consensus is not that these were valid microfossils, this was a reputable report that was taken seriously, and it did get a lot of people in the field of planetary science and adjacent fields to say, well, why not? What's so outrageous about that? Everything we know about Mars, everything we know about the origin of life is consistent with the possibility that there could be microfossils on Mars. So this and the public reaction that I think helped NASA see that, oh, people are really excited by this stuff. They don't see it as flaky. It's not going to be a threat to our support. Congress and the public are genuinely excited by the prospect of discovering life elsewhere. All of this led to a sea change, and astrobiology became a field well supported by NASA and around the world, a community, interdisciplinary community of astrobiology, which continues today, began as really a new kind of hybrid science. So astrobiology at NASA, you could divide it into phases. From the beginning of exploration until the formation of the Astrobiology Institute in 1998, it was exobiology, which, as I mentioned, was of interest and supported to some extent, but not really seen as central. In 1998, in the wake of all of this I've been describing, NASA formed the Astrobiology Institute. And for 20 years, that entity very successfully helped to foster and build up this field. It became a global, it's an international effort now, but the NASA Astrobiology Institute was really key in supporting early career researchers, in facilitating communication with the public, in really developing a new way to be interdisciplinary as is needed for this effort. And the Astrobiology Institute was kind of concentrated in a relatively small number of teams. And after 20 years, in 2018, the Astrobiology Institute was disbanded in favor of what we now call the Astrobiology Program at NASA, which is supported at about the same level, but is a little bit more distributed into a larger number of teams and connected through what we call the research coordination networks. And just really briefly, research coordination networks include on the upper left there, the Nexus for Exoplanet System Science. You've been hearing about exoplanets. We'll hear a little bit more about that. The PCE3 is basically the group that studies the origin of life and how that emerges from early environments. On the right there, the Network for Ocean Worlds, that's pretty self-explanatory, but it involves a lot of collaboration between planetary science and earth science, oceanographers, and really applying what we know about oceanic environments and processes to our study of other worlds. Down on the left there, N-Fold is the Network for Life Detection, the community that studies both the technology, the engineering, and the science of life detection and tries to fold in our growing understanding of life and look for agnostic ways. How do we search for life and not just assume that it's exactly like life on Earth? And finally, on the lower right, the Life RCN is really studying the early evolution of life and the interactions between planetary environments and evolutionary processes. So one thing about NASA science is that it's divided into these 5 divisions, all of which do amazing work, which are sometimes seen as separate efforts. And of course, you need some division into science topics in order to support work and go forward. But there's always a risk of the sort of siloing effect you want to make sure that the people in these groups are working together on projects that can benefit from the perspectives of all. And astrobiology turns out to be an amazing sort of connective tissue for these efforts. So even though astrobiology kind of grew out of planetary science, what we're doing at NASA now is really shoring up and expanding the connections between all the different divisions, using astrobiology as that kind of connective tissue. And that's a lot of what I'm trying to do in my new role as a senior scientist for astrobiology strategy at NASA. And there's some obvious areas, exoplanets, they don't fit just within planetary or astrophysics, and ocean worlds, they don't fit just within earth science or planetary. And of course, helio is very important for all of our notions of habitability and how stars evolve over time and the effect of stars on on planetary environment. So there's really a lot of connection that can be utilized and fostered through astrobiology. And just a couple examples of some of those connections that we're working with. In the earth science connections, I mentioned ocean worlds. There are hydrothermal vents that we can study on Earth's floor, and we believe there are hydrothermal vents also on the rock-water interface on Europa that are much harder to get to than the Earth ones. So that study is very important. Ice-water interactions. Ocean drilling is something that we're actively looking at, how planetary scientists and earth scientists can work together to use those drill cores to gain new insights about the way ocean and planets work in general. Climate cycles, biogeochemical cycles are all aspects of other planets that we can study on Earth and apply to elsewhere, and also gain insights about our own planet from the comparative planetology efforts. And of course, in astrophysics, as we've just been hearing, now with the exoplanet revolution, we need the detailed insights that we get from our own solar system to understand what we're seeing on exoplanets, and we need the diversity of exoplanet environments to put our own solar system in context. And especially with biosignatures, we are getting more sophisticated about going beyond just saying, oh, that's an interesting gas that could be associated with life, to, well, what are the geophysical and geochemical and biogeochemical processes that could be affecting that gas, and trying to look at planetary system science and see biosignatures in that context. And for that, of course, we need the connections with astrophysics and other fields. So the last thing I want to say, I haven't even been looking at my time, but I bet I'm just about out of my time, is that all of this theorizing we do, it's a very speculative field. The notions of life elsewhere is important and fun and exciting, but the way we learn is through exploration, the way we nail down the actual prospects for life elsewhere. And so this is a slide actually that Sean Domingo-Goldman put together out of some conversations we had. You know, we talk about our planetary fleet and our astrophysics fleet, but really for astrobiology, our fleet sort of looks like this, where we absolutely need our astrophysics observatories, our current ones, JWST, in the future, Roman and HWO, and we also gain from all of our ongoing planetary science missions, current ones and the future ones. We're really excited about our Dragonfly going to Titan, as I mentioned, Clipper launching later this year to Jupiter. And also, you may not think of it, but we have Da Vinci and Veritas that are going to go to Venus. And in my mind, those are, at least in part, astrobiology missions as well, because characterizing the past history of rocky planets on our solar system and understanding how planets that may have once been habitable have lost habitability, and what the timescales and processes were for that, that's going to really help us when we start to see Mars-like and Earth-like and Venus-like planets in other star systems, and try to understand how their nature and their history fit in with the detailed histories we can infer from our solar system. So this astrobiology fleet is what really excites me about the present and future of astrobiology as a multidisciplinary, multi-divisional quest within NASA. And there I think I'm definitely out of my time.
David, thank you so much.